Today's lesson on TypeScript is designed for quality assurance engineers. We will start off by talking about how TypeScript can reduce the amount of testing that you would need to do for your code, followed by a custom tour of the TypeScript programming language designed specifically to reduce the greatest amount of bugs with the smallest amount of type annotations required. The common objective of most forms of testing is to reduce the number of bugs that exist within our code. And when we talk about bugs, not these kinds of bugs, these kinds of bugs. The things that make our code go bang and our users to have a bad experience. And as you can probably tell from this screenshot, specific to this particular talk is everyone's favorite programming language, JavaScript. This is most likely the programming language that your web application is using, and more increasingly, what you are using to test your applications as well. And this is a programming language that is filled with things that make you go, what? Instead of something like horse cat, you end up with something like, I don't know what this is. Now, before we continue, one thing that I want to emphasize is that many things within JavaScript will throw an error if you do something stupid. What is even more interesting, specific to this particular error, is that even though JavaScript is a dynamic language, it does throw this thing known as a type error. So it's not that JavaScript is completely untyped, it's just that it's typed at runtime instead of compile time. Now let's do a quick recap of some of the features of JavaScript. Consider the simple example of adding two arrays. What do you think would be a good answer for the JavaScript runtime to return for this particular case? A nice thing would be something like an empty array, or if array addition is something that is not supported within JavaScript, a good answer would be something like a type error, which we saw previously when we tried to invoke a function that did not exist. However, JavaScript in its infinite wisdom and 1 week of delivery deadline decides to return an empty string. I know. What? And I'm not even going to make you guess what the answer is going to be in this particular case, because you will never guess it. It's this weird string, which is basically the string representation of just an empty object. And now that you understand what an array plus object is going to be, it is pretty obvious that you should also understand what object plus array is, because by laws of math addition, the order of the operators should not matter. But this is JavaScript, so you get exactly what you would expect, which is the number 0. And of course, you might argue that this is a particularly weird example, and I'm not going to disagree with you, but these kinds of errors do show up in production code. No one might ever write the direct addition between an array and an object, but we normally don't write direct code. Most commonly, you will be working with some variable that is coming from an API of an API, and by the time that we are invoking the function, we have no guarantee that the types are going to be what we expect them to be. So instead of writing silly code like this, and not getting any errors, the key objective of TypeScript is to enforce a compile time type system which will catch these as compile time errors. And before you think, oh my god, I have to learn a completely different programming language, not exactly. All of your JavaScript knowledge is still applicable to TypeScript because TypeScript is simply a superset of JavaScript with some type annotations to help you catch errors at compile time. And that is exactly what we will look at in this session. And it's almost impossible to mention anything about type safety without getting into an eternal debate about dynamic versus static typing. And one key argument against a compile time type system as offered by TypeScript is that we have unit tests. And while there is definitely some truth to that argument, we all know that we can take as much help as we need to make sure that our systems continue to function the way we expect them to. Now I can go on and on about all of the reasons why within the static versus dynamic debate I am in the static camp. But that's not what you're here for. My promise to you for this session is to make sure that if you are familiar with JavaScript, you are going to be comfortable with TypeScript by the end of this session, and that type annotations can help reduce the amount of testing that you will need to do. Here we have a simple piece of JavaScript code where when a function called sendEmail is invoked, it makes sure that the email is actually present, like not null or undefined, and then it is of a type string, that is not a number or some object. And then I've redacted the body where it would actually send the email. Now you might think that this initial check is a bit weird, but this is actually from a real world code example. And you might be wondering why this particular validation on the input exists. Well, because in addition to a correct call, there were also incorrect calls. For example, a misspelling in email, in addition to just straight up forgetting to add a .email at the end, or even using the wrong property, for example .id, and expecting it to magically work. And because these are genuinely good developers making simple silly mistakes, They also made sure that this particular issue does not arise in the future by adding tests to make sure that an undefined value throws an error, an object instead of an actual string will throw an error, in addition to the happy case where the function is actually invoked with the correct email string instead of some random garbage. And fortunately, when we migrated that code to TypeScript with the simple type annotation marking email to be of type string, we found that we didn't need that initial statement which was doing the check for a correct type anymore. With this simple signature, a call with the correct string would be perfectly fine. However, if you make a simple typo, for example, misspell email, that would get caught at compile time by TypeScript. In addition, if you provided an object, it would complain. If you provided a value that was not a string, for example, ID is of type number, that would complain as well. So because of these invalid calls getting caught by TypeScript at compile time, we do not need that runtime check within our function body anymore. And then the same thing for our tests. When we migrated them over to TypeScript, when we had those calls for undefined or a call with an object instead of an actual string, TypeScript would catch that at compile time, and the only check that we would really need is that check with an actual string value. The other ones became errors and we safely removed them from our codebase. Now that we've taken a slight detour into understanding that TypeScript truly does help us reduce the number of tests that we would need to write, let's take a step into the basics of the TypeScript programming language. Now we've already seen string annotations, which are, no surprise, used to annotate strings. There are additional primitive types within JavaScript, and TypeScript does have annotations specific for all of these as well. These include the boolean true or false, the number type which can take any integer or a floating point value because numbers within JavaScript are always 64-bit floating point, a type for the special value undefined, which is normally used to represent something that hasn't been initialized, the special annotation for the null value, which is normally used to represent an end of a chain or a value that is currently unavailable, as well as special annotations for the modern symbol type, which is used to communicate across domains or create special unique values and non-iterables. That's a whole topic in its own, as well as an annotation for a big int, where you can store as big an integer as you want as long as you can fit it in memory. The key takeaway over here is that all of the primitive types that are present within JavaScript have a special type annotation available for you to use within TypeScript. Now, the objective of using these annotations, of course, is to keep you from making silly mistakes. For example, if you annotate something of type number, you cannot assign anything other than a number to it. For example, if you assign a string to it, it will get caught at compile time by TypeScript. Now, what we have also seen in that basic example that we started with is that when we have a function that has multiple parameters, we can use type annotations for parameters as well. And as we saw previously, this can be used to catch the silly mistake of calling the function with an object of the wrong type. With the primitives out of the way, the next thing to look at in the hierarchy of data manipulation is JavaScript objects. Here we have a simple JavaScript object called center that has two properties, x of type number and y of type number. Now TypeScript has special syntax for annotating objects, and it looks very similar to how you actually write the objects in JavaScript. Here we are saying that center is going to be an object as indicated by these curly braces, which is going to have a property x of type number and y of type number. Now if you are using the same structure of an object in multiple places, then it can become quickly cumbersome to have to do the same annotation again and again, and that brings us to the next thing within the TypeScript toolbox called type aliases. You can actually take any annotation that you have within TypeScript and then give it a special name using a type alias. Here we are saying that point is going to be a type that is always going to be an object with members x of type number and y of type number. And with this type annotation created, instead of having to do this annotation again and again, we can simply use the type alias. Now, one thing that is definitely worth mentioning when we are looking at types for objects is optional properties. Within TypeScript annotations, you can add a question mark after the property name to indicate that it is going to be an optional property. Here we have a person where email is going to be optional, which means that it is perfectly valid to have a person where email is not specified, just as it is valid to have a person where the email is a valid string. However, if you provide something that is not a string, that is still going to be a compile time error. An optional string basically means nothing, or a string, everything else is still invalid. Now, talking about type aliases, we mentioned that we can use anything that is present within a type annotation and give it a type alias, which means that you could use even something primitive like a string and give it a new name. And this would work perfectly fine. You could use the primitive string annotation or this newly created str type annotation. And as far as TypeScript is concerned, the built-in as well as the custom type are going to be exactly the same, which means that you can assign one to the other. There will not be any type error, but please don't do that. Use type aliases when they make sense, and try not to use type aliases to create your own custom programming language on top of the existing TypeScript programming language. But this is a great example of demonstrating the power that exists within the TypeScript type annotations. Now we've already looked at how you can annotate objects within TypeScript. Another thing to be aware of that is closely related to the concept of objects is arrays. Now here's a pro tip: whenever you have a variable that is initialized with the value, you can actually hover over it to see what type TypeScript has inferred for it. And because we are initializing with an array, this gives us what the type annotation should be for an array, and if we paste that in, it's going to work perfectly fine. When we say that we have an array of numbers, it means that we can have as many numbers as we want. We can have no elements, 1 element, 5 elements. These are all perfectly fine. But all of these members must be numbers. If we give it an array where some elements are not numbers, for example, here we have an array of 1 element of type string, TypeScript is going to catch that error at compile time. One more thing worth mentioning is that when we annotate something of type array, we get access to all of the methods that exist on an array as well. For example, here we are using array.map to map the values into their squares with x power 2. And that's pretty much all that we need in order to start using arrays within TypeScript. The next thing that I recommend that we look at is taking a deeper look within functions, because JavaScript is very much a functional programming language, and using functions effectively is at the core of being an effective JavaScript developer. Now we've already looked at how we can annotate the parameters for a function. The next thing that we can look at is how we do a return type annotation. And the same trick that we saw for an array, we can actually hover over the function to see what TypeScript has inferred and the kind of syntax that it expects for a return type annotation. And if we just copy what it has inferred and put that into place, it will work exactly as you would expect. We have just annotated the add function to always return a value of type number. Now there is another reason for looking at this return type syntax in isolation, and that is because some functions don't actually return a value. For example, here is the log function that simply logs whatever is passed in and does not return a value back to the caller. And we will do the same trick that we did for the add function, where we hover over the log method to see what annotation TypeScript expects, and it expects a void annotation. The void type is a special type within TypeScript designed specifically to annotate a function that does not return any value back to the caller. Now we spoke a bit about TypeScript and JavaScript being a functional programming language, and a key trait to satisfy this requirement is to allow first-class function, that is, functions that can be treated as variables. So instead of creating the function outright, we can easily just create a variable called add and then assign it any add function that we want. And this is perfectly valid JavaScript as well as TypeScript. However, what if we want to annotate the add function upfront? This brings us to the declaration specifically within TypeScript for function variables. Here we are saying that add is going to be a function that takes a and b of type number, and then it will return a value of type number as well. The usage of an arrow for a return type annotation within TypeScript closely resembles the usage of an arrow for the return body of an arrow function within JavaScript. Now we've said this 100 times before, but let's just say it again. You can always take anything that is present within a type annotation and give it a type alias, which means that we can use this particular function's signature and give it a type alias called add. And then instead of having to annotate whenever we need an add function, we can simply use that type alias. Now types for functions show up all the time in the real world when you are working with libraries. For example, here we have a type called incrementable that has a member called increment, which is going to be a simple function that returns void. An example incrementable would be a simple object that contains an initial value and then an increment function which increments the value by 1. Another common pattern that is present within JavaScript is having a function that takes one or more types of arguments for the same parameter. For example, here we have a function where the input might be a single string value or an array of string values. Now, if you don't give any annotation to the input value, it would leave it open to providing pretty much anything. So someone could even provide a number by mistake. So in order to prevent that, we need some annotation on input, but we can't annotate it as a string because that would make the string array an error, and we can't annotate it as a string array because that would make the string argument as an error. Fortunately, TypeScript has this thing called union types. They are represented by the simple pipe operator, and here we are saying that input is something that can be a string or it can be a string array. That is the union of a string and a string array. With this annotation in place, the string and the string array arguments are allowed. However, when we provide a number, that is caught at compile time as a mistake. Within various JavaScript apps as well as APIs served on the internet, there are some specific strings that hold special meaning. For example, direction might be something that only accepts north and not some uber late misspelling of norths. For this purpose, TypeScript has this thing called literal types. Instead of saying the direction is a string, we can say it must literally be the string north. And with this annotation, the uber lead spelling gets ruled out as a type error. Now, this might not look like a particularly useful use case, but that's because literal types are quite commonly used with the other feature that we just learned, which is union types. So here we are saying that direction must be one of the literal strings, north, east, south, west, and anything else is ruled out. So you can assign the string south to it, but of course that lead spelling is still an error. And just to be even more specific, you probably wouldn't annotate a variable with these particular annotations. You would probably create a type. For example, if you are talking about north, south, east, west, you would probably give it a name like cardinal direction. Additionally, the ability to have literal types as well as union types allows us to be extremely expressive with a lot of JavaScript code out there. For example, we can declare a square as something that has a kind of square and a size of number, a rectangle that has a kind of rectangle and a width and height, and then a shape can either be a square or a rectangle. This allows us to have utility functions that can operate on all kinds of shapes. For example, an area function that takes a parameter of type shape, checks if it is of kind square, and then returns the square area. Otherwise, it checks if the kind is rectangle and returns a rectangle area. Now, you've probably seen JavaScript code like this area function, but what's missing within this code is the context about what does a shape mean. It means either a square or a rectangle, which you can only annotate effectively if you are using TypeScript, and this is great documentation for someone else that might be confused by what the hell is going on within this area function. Let's talk a bit more about the nature of the type system of TypeScript and specifically the fact that it is actually a structural type system. What that means is that TypeScript really strongly cares about the structure of your objects and not necessarily their name. For example, here we have a type alias for a user, which is going to be an object which has a member ID of type string, and a type alias product which has exactly the same structure. Now, if we create a variable and explicitly annotate it to be a user, and then we create a product annotating that to be a product, as far as TypeScript is concerned, because the structure of the two types is the same, these two variables are of the same type, which means that we can assign a product to a user or a user to a product without any compile time errors. Now, if TypeScript was a nominal programming language, the names of the types would matter and we would not be able to assign a user to a product or a product to a user. But TypeScript is intentionally designed to be a convenient programming language and not a painful type-safe language full of overhead ceremony that you might have experienced in the past. Let's take a look at why this structural typing is actually useful. Here we have types representing a point in 2D space with member x and y of type number and a point in 3D space with x, y, and z of type number. We create two reference variables, one of type point 2D and one of type point 3D. Now, because of the structural nature of the TypeScript types, even though we haven't declared any hierarchy between a point 2D and a point 3D, TypeScript is going to understand the fact that a point 2D is essentially a subset of a point 3D, which means that anything that is of point 3D can be safely assigned to something of type point 2D. And this will be true even if we try to invoke a 2D function with a 3D point. This is because a 3D point satisfies the structural constraints of a point 2D, that is, it has an x of type number and a y of type number. And even though this might sound scary, which will result in some weird issues at runtime, that's probably not going to happen because it is not going to allow you to assign a point 2D to a point 3D because it is missing the z value which is required for a point 3D. And this check, of course, will also apply if you try to invoke a function that expects a point 3D and try to pass in a point 2D. Now, there is a lot more that we could talk about in terms of structural typing, nominal typing, and how you can mimic one with the other, but all of that would be useless if you didn't have an easy migration path from your JavaScript to TypeScript. So let's talk about two key types that help you with this migration. Now, the first one of these, known as the any type, was specifically designed to give you the easiest, most painless process for migrating from JavaScript to TypeScript. To demonstrate how any behaves within the type system, we have a simple variable that is annotated as type any. Now, fundamentally, any is something that can accept any value, which means that you can assign it a number, a string, or anything else that we have within the type system. The key objective with any is to give you as much freedom as you want with this variable so that you can easily simply annotate any JavaScript variable as any and then do pretty much whatever you want with it. This means in addition to assigning whatever you want, you can actually read it as literally anything. You can invoke functions on it that may or may not exist, and even assign it to variables within your code that might have well-defined types, for example, assigning it to a boolean. TypeScript will go to great lengths to get out of your way and let you do whatever you want with a variable of type any. Now, as you can imagine, this much freedom can quickly get out of hand, and for a long time, this was your main process for migrating from JavaScript to TypeScript. Either you started giving specific annotations to everything, or you gave a few variables and an annotation of any, and then pretty much suffered the consequences of having pretty much no type safety within your code base. But fortunately, that's changed in modern TypeScript, and there is an additional type that you can use that provides a nice balance between any and strong types, and that type is known as unknown. So let's look at the same example, but this time instead of using the any type, we create a variable of type unknown. Now, unknown does offer a similar level of convenience as any in a number of ways. For example, you can assign anything to it. You can assign a number, a string, or an object, or whatever else that you want to an unknown variable. However, a key difference, and that is sort of indicated within the name as well, is that TypeScript will sort of prevent you from unsafely using this variable and treat it like an unknown. So if you try to, for example, invoke a string method like trim on it, it's going to complain, I don't know what this is, so I'm not going to let you invoke a function on it. Similarly, if you try to assign it to a boolean, it's going to complain, I don't know what this is, I'm not going to let you set it to a boolean. This doesn't mean that you can never use an unknown variable. What this means is that you have to use some form of a runtime check to make sure that you know what the variable is before you use it. Let's take a look at the example. If we think that the value is currently going to be a string and we want to use the trim method, then we have to use a runtime check. For example, type of example unknown is equal to string, and then TypeScript will happily let us use the trim function, which is something that exists on strings. Similarly, if we think that it is a boolean and we want to use it as a boolean, for example, assigning it to another boolean, then we can use a runtime check, that is type of example unknown is equal to boolean, and if that turns out to be true within that conditional block, TypeScript will happily allow us to assign it to a boolean value. So the lesson over here is that use the any type to conveniently, however a bit unsafely, migrate your code over from JavaScript to TypeScript. However, if you do care about type safety, then you can use explicit type annotations, or for a makeshift option, use the unknown while you are still discovering what the different variables are within your code. Now, the next step is to set up a development environment where you can start practicing what you have learned about TypeScript and start executing TypeScript in the real world. Now, I'm going to assume that you already have Node.js installed, but it's pretty easy to do. You go to Google, search Node.js download, and from the download page, download the installer for your operating system, and then go through the guided walkthrough provided by the installer. And once we have Node.js installed, we can use it to create a new TypeScript/JavaScript programming project. We start off with an empty directory, and Node.js comes with this script called npm, which is used to download packages, and we use that to initialize a new package.json, which is what will be used to maintain our project over time. The only package that we need for TypeScript is TypeScript, and we install that by running npm i TypeScript. With this package installed, it gives us access to this thing known as the TypeScript compiler, which is provided as a CLI command tsc, and we can execute that from the installed version by running npx. Npx is something that came with Node, tsc, and then provided a couple of options to initialize the new ts config. We use --init. All of our source code will be located in the src folder, and for that we use root dir. The output will be generated into the lib folder, and for that we use out.dir. And to be able to debug TypeScript from the generated JavaScript, we provide the command line flag --inline source map, and then we will generate the most modern version of JavaScript that can execute, because we will be running in Node.js, which is a fairly modern version of JavaScript. So we specify that with --target es next. Now there is a nice link that it prints out which you can use to learn more about these options. But anyways, continuing with the tutorial, we will open this folder up within our IDE and we are going to be using VS Code, which is a free IDE provided by Microsoft, and it's fairly popular with a lot of developers nowadays. Now, as we specified in the options, we are going to have our source code within the src folder, and we create our first source file called index.ts within that folder. Now, this is not going to be a hello world tutorial. Instead, it's going to be a hi fam tutorial, and that is what we will log to the console using the built-in JavaScript console.log. Notice that this file is a .ts or a TypeScript file, and Node.js runs JS or JavaScript files. So the first thing that we will have to do is to compile this TypeScript code into JavaScript, and for that, once again, we will use the TypeScript compiler and execute that with npx tsc. And it will automatically pick up that there is a config file over here. And within that config file, we know that there's the src folder containing index.ts. And it's going to take that source file and build it into the ouch.dir lib folder. And within that folder, we will get index.js corresponding to this ts file, which we can execute with node lib/index.js. And no surprise, you get to see the console message. Now, running the build script again and again might become a bit tedious. So fortunately, what we can do is we can create a build command within our script section within package.json and then invoke tsc, but this time with the ---- watch flag. This will leave tsc running in watch mode, so we don't have to run the build again and again, and we can leave it running in watch mode in the background. And then to execute our built JavaScript, we will create a simple script called start, which will invoke node passing in the path to our entry point, which is lib over index.js. With these two scripts created, when we want to start our development, we open up the terminal and execute npm run build. This starts TypeScript in watch mode, and we leave this terminal open, and whenever we want to execute our code in a new terminal session, we simply run npm start. Now, we are not using any TypeScript syntax, and this was sort of intentionally to prove the point that you can use your JavaScript within a TypeScript file. But let's use some TypeScript syntax. Let's create a variable message of type string, give it this particular string value, but just to see a different output, add some text to it, and then log this particular message variable. And now, because the TypeScript compiler is running in the background with that npm build command, when we run npm start again, it picks up these latest changes and we see the new message logged to the console. I'll wrap things up there. Hopefully you've learned some of the advantages of using types in order to test your code at compile time without having to run them like you would have to do with traditional tests. You're familiar with most of the syntax of TypeScript, so you can see it in production and not get surprised. And finally, you have a development environment set up to play around with TypeScript to learn more.